speakers. The first will be Noelia Sanchez Gonzalez from Oxford University, who will tell us about superstring phases in the early universe and gravitational waves. Please take it away.
Thank you so much. I'm very happy to be here today talking. So my name is Noelia Sanchez. I'm doing the PhD in Oxford under the supervision of Joseph Conlon and Edward Hardy. And today I'm going to be talking about some work done in collaboration with them, together with Edmund Copland in Nottingham. Okay, so we'll start reviewing the motivation behind this work in the introduction. And then my goals for today are basically two. We'll talk about the results that came out in a paper earlier this year in May, in which we perform a dynamical system analysis that I'll describe in a second. And then to talk about the study of the gravitational wave signal associated with those results that came out last. Okay, so let's talk about cosmic strings to start with. Cosmic strings are these one-dimensional structures that reach cosmological sizes, and they are characterized by their tension, so their energy per unit of length. Today, I'm going to be talking a lot about tension, so keep that concept in mind. And then cosmic superstrings refer to fundamental objects in string theory that can behave as cosmic strings. For example, we have the F strings, the fundamental strings of the theory, and one can also have effective strings. So branes wrapped around internal cycles such that from the four-dimensional point of view, they look like one-dimensional objects. Now, as any other coupling and physical scale in the theory, the tensions of these objects are going to be set by the moduli, the scalars controlling the compactification, and different types of cosmic superstrings will have different dependencies on the moduli. Now, in the early universe, moduli could be evolving. So during inflation, they could be displaced from their post-inflationary vacuum. And then once this one stops and Hubble friction starts dropping, then they can start rolling towards their current minimum. So if we have moduli evolution and the tensions are set by this moduli, one can expect to consider time-dependent tensions in the early universe. In some earlier work, we actually studied the evolution of subhorizon cosmic string loops that have a time-dependent tension. And what we found is that they actually follow the physics of a rubber band, in the sense that if you can imagine a rubber band, if the tension of it increases, the rubber band will want to shrink, and vice versa. If the tension drops, it will want to grow. And this is precisely what these subhorizon loops with a decreasing tension do. This is in contrast with the standard fixed tension picture, in which they would basically shrink over time due to their gravitational emission and eventually disappear. So this drop in tension leading to a physical growth is what allows them to persist and is one of the key ingredients in the results that we'll discuss today. Okay, so when I say early universe, how early do I mean? We know we have observational constraints on the first stages of the universe from Big Bang nucleosynthesis, BBN, and the cosmic microwave background, CMB. And in particular, from BBN, we know that the equation of the state of the universe at that point has to be radiation dominated. And so the standard cosmological history is that after the early inflationary era ends, it is followed by reheating into relativistic standard model degrees of freedom, and then the universe becomes radiated dominated from that point onwards. However, the equation of the state of the universe before BBN is actually unconstrained. And so the idea is to think about whether one should expect string phenomenology to take a role there and what kind of stringy physics one can expect. And in particular, right, one question that one might ask is, how long is this era? Well, quoting this recent paper, this era might be up to the first half of the universe in logarithmic scale, meaning that it might span timescales over 30 orders of magnitude. Okay, so this is the period of time in which we're going to be thinking about string phenom. Now, what string physics can one expect? So I've mentioned that one can find rolling moduli after the end of inflation. And if that is the case, if there was an initial population of cosmic subhorizon loops there, then because of the rolling moduli, if the tensions decrease, these will start to grow in physical size. Now, in this talk, I will not enter to discuss the origin of this population, but as production mechanisms for it, one might think of nucleation from the vacuum at the end of inflation, or as byproducts of deep brain annihilation. Now, at some point, the moduli reach the current vacuum, and as they settle into it, they oscillate. So we enter a period of moduli oscillations, which is a very general expectation in string cosmology, this early era of moduli domination, in which the universe is matter dominated. Now, once the moduli start to oscillate around their minimum, the tension of these loops becomes fixed and they start to shrink due to their gravitational emission. Eventually, the moduli decay, reheat the universe with the relativistic standard model degrees of freedom, and by then these loops have disappeared and what remains is their gravitational radiation. And then this would be followed by the standard cosmological history, and so it has to happen before BBN. Okay, so with this evolution in mind, we're going to consider the following system. Okay, we'll start with an FLRW background described by its scale factor. We'll consider a scalar field, a modulus with a certain potential, and on top of that, we'll add a population of cosmic subhorizon loops that, as I've mentioned, right, they're going to have a dependence on this modulus through their tension. So again, the idea is kind of to assume that this population is there and see if it changes much the big picture, the global evolution of the system. Okay, so for that population, we're going to parameterize its dependencies like this. There's going to be a scale, a factor a to the -3. Now, this is just accounting for the fact that the number density of this population is getting diluted by the expanding volume. So we are considering these loops to be isolated from each other and neglecting interactions. And so the way they feel the expansion is through this scale factor. Now, the dependence with the canonically normalized modulus is going to be through an exponential. And in this talk, I will discuss the results in the case of F strings, for which that coefficient beta takes this particular value. For the scalar field, I'm going to be thinking about the volume modulus, and its potential will take it as an exponential with a certain slope. Now, again, I'm going to be focusing on two particular cases. The potential corresponding to the large volume S scenario, which allows the volume to be stabilized at exponentially large volumes in string units, as you know, which has the exponential part has a lambda with that particular value. And we'll also study the case of a canonical potential in the sense of being set by the string scale only, for which the corresponding lambda is this value. Now, note that the lambda in the case of LVS corresponds to a steeper exponential with respect to the canonical case. And this is going to have consequences in the results that we'll see in a second. Okay, so we have that system. Now let's look at its equations of motion. So to start with, we have the Freeman equation, right, in which here in the right-hand side, you can see the different contributions to the total energy density. You have the kinetic energy and the potential energy of the scalar field. And then you have the energy density contribution from the loop population. Now, on top of this, we have the two continuity equations for the modulus and the population of subhorizon loops. And here you can see the terms in red are the new coupling terms due to this dependence of the loop population on the modulus. Now, in the standard fixed tension scenario, in which those coupling terms are not there, if we had a subdominant population of subhorizon loops, then they shrink over time, release their energy into gravitational radiation, eventually disappear, and do not change the whole picture much. However, we're going to see that these coupling terms are going to allow this population to back react on the evolution of the modulus in a surprising way. Okay, so before doing the dynamical system analysis, we need to do a change of variables. And so we're going to be working now with X, Y, and Z that relate to the energy density fractions like this. So the X is related to the kinetic energy density, Y is related to the potential energy density, and Z is related to the fraction energy density in loops. And as energy densities, the fractions, they have to sum up to 1. Once we rewrite our equations in terms of these variables, turns out that the system looks like an autonomous system, meaning that time does not appear explicitly in this right-hand side. And so once we have this, our goal is going to be to find the fixed points for our system, meaning the points at which the evolution stops and these energy density fractions become constants. Okay, so let's discuss the results. In the case of F strings in the large volume scenario, we have this phase space diagram. X is the kinetic energy density fraction, Y the potential, Z the loops. And they have to sum up to 1, and so they have to move inside this circle of radius 1, right? Now, when one looks at this phase space diagram, one can see that there is an attractor point, B, which we call a string loop tracker, in which 3/4 of the energy density of the universe is in the form of these subhorizon cosmic string loops. This means, right, these diagrams tell us that if we start with any initial distribution of energies with a non-zero contribution in the form of loops, then the evolution, given enough time, is going to go towards this string loop tracker. Okay, maybe also a time evolution picture helps here. Here we can see how an initial small energy density in the form of loops is growing and gets driven up by the evolution to a 75% of the energy density of the universe. Yeah, now, in the case of a canonical potential, so we can do the same, compute the fixed points, and the phase diagrams now look like this. Now we can see that there is an additional fixed point, which we called mixed tracker, in which there is some non-vanishing energy density in all the different fractions, still with a significant fraction of energy in the form of loops that did not appear before. A bit of physical intuition, right, for why we have this fixed point now in the canonical potential case is the fact that the potential now is not as steep as in LVS. And so the potential energy density fraction is able to keep up with the other two components, and there exists a fixed point in which they all remain a non-vanishing fraction and redshift in the same way. Okay, in the paper, we also consider the case of a background radiation fluid being present, and with the question of, okay, is this going to change much, the picture that we found? And turns out that in the case of F strings in LVS, the final attractor is still the string loop tracker with 75% of the energy in the form of loops. So the loops are actually growing with respect to the background during the radiation tracker. But it is an interesting scenario because this background radiation fluid might help avoid the overshoot problem, because it helps keeping the potential contribution non-zero. And so if the modulus approaches the minimum, once the potential energy is still significant, then it can get trapped in the minimum, and it still have a fraction of the energy density in loops. For some for more discussion and more details on the overshoot problem in this context, there's also a very recent paper this year. Okay, and now we can move on and talk about the gravitational wave signal associated with these new attractors that we found, right? So what is the evolution behind the signal I'm going to discuss? So the starting point is going to be this string loop tracker. So we found this solution in which an order 1 energy density fraction of the universe is in the form of cosmic superstring loops. And that is going to be our starting population for this gravitational wave signal. Now, as I said before, once the modulus reaches the minimum, it will start to oscillate around it. And at this point, the tension of the loops becomes effectively fixed, so they start to shrink due to their gravitational emission. Now, except for this gravitational emission loss, the loops now behave as matter. Their tension is fixed, and they only sense the expansion through the expanding volume. And so they behave as matter, and so does the energy density associated with the moduli oscillations. So we have a matter-dominated universe at this point. At some point, though, the cosmic strings are going to completely evaporate, and we're going to enter a period of moduli domination, in which these oscillations that behave like matter redshift the gravitational radiation that has been emitted. Right, radiation goes as a⁻⁴, matter goes as a⁻3. So these gravitational waves start to redshift during this era. And therefore, the shorter this era is, the better chance of having large amplitudes for our signals and having a potentially observable signal. Okay, and at last, we know that the moduli has to eventually decay, reheat the universe. This has to match the standard cosmological history at BBN. And so the gravitational wave radiation that has been emitted will remain as part of the dark radiation content, and therefore has to satisfy dark radiation bounds at BBN. Okay, what about the gravitational wave emission from these loops? So the frequencies at which they emit are related to their sizes. Bigger loops are able to emit lower frequencies. And once their tension gets fixed, then they have a certain lifetime due to this gravitational emission, right? Basically, the time it takes to them for them to radiate this energy, their energy away. And that is set by their length and by their tension. So smaller loops decay faster, and if they have a bigger tension, they also decay faster. Okay, when computing the signal from this scenario, one should keep in mind that the string loop tracker assumed isolated loops. So there's going to be a bound on the length that we are considering for this population. Now, the gravitational wave power spectrum is the energy density fraction that reaches us today per logarithmic frequency interval. And so the way we compute it is we're going to do an integral over the duration of the emission. Here, Ti is the start of moduli oscillations, and tau denotes the lifetime of the loops. And we're going to integrate over this period of time the energy density emitted per unit of time and per unit of frequency, such that this is the total energy density emitted per unit of frequency. And then we have this additional redshift factor, right, as the signal gets emitted and travels to us today. An important feature of this spectrum is the fact that it presents a peak, and that peak corresponds to the moment the loops decay. So the loops lose most of their energy at the end of their lifetime. Therefore, the main idea behind the best case scenario is that, well, this scenario is attractive to start with because we have a lot of energy stored in these loops that is going to get released into gravitational waves. This is in contrast with the case if we had a network of cosmic strings that was in a scaling regime. Actually, its fraction of energy is suppressed with respect to the background with a factor of order extension. So this is already a good scenario, a lot of energy that is going to get released. And on top of that, subhorizon loops behave as matter. And so as long as this energy is stored in them, it's not getting redshifted with respect to the background. And once it gets translated into gravitational waves, then it's going to get diluted during this early matter-dominated era. So the longer they survive, the better. Now, with this in mind, we computed the signal in the context of a fast moduli decay, which allows for shorter moduli domination eras. In particular, we consider the decay rate presented in this paper, which basically gives an enhanced decay rate due to an enhanced coupling to the Higgs sector in the context of high-scale SUSY. And now also in LVS, right, we know that parameters such as the mass of the modulus or the tension of the strings are set by the volume of the compactification, and they are not independent. So we have this parameter, this one parameter governing our signal. Also, for more aspects of gravitational waves from cosmic superstrings in the context of LVS, there's this recent nice paper. Okay, so our gravitational wave signal looks like this. We have this population of isolated subhorizon loops that start being an order 1 of the total energy density. And then the color lines correspond to this scenario in the context of LVS with this fast decay rate, in which here it has an enhanced factor with respect to what would be the normal gravitationally suppressed decay. So we have an enhanced decay rate that allows for larger amplitudes as the signal gets less diluted because there's less of a moduli-dominated era. And the dashed line actually corresponds to the case in which if the moduli decay fast enough such that the loops survive until the end of moduli oscillations, so until the time of reheating, then this signal can saturate the dark radiation bounds from BBN. Now, the microphysics for that decay are not yet known, but we highlighted here as the best case scenario for the large amplitude. We can also see, right, that this signal is peaked at high frequencies, as is the case also for other early universe signals. Okay, and now let's recap a bit the results that we've discussed today. So I started motivating the study of a string pheno in the early universe, right? Because we found there this unconstrained periods of time where one can expect for some string physics to actually be taking place. For example, right, moduli could be evolving, and if that is the case and cosmic strings were present, then they would feel time-dependent tensions and have different dynamics than we normally expect. The main results we've presented, right, are the existence of these superstring phases as attractors, these phases with so much energy in the form of cosmic superstrings. And then we've also talked about how gravitational waves can be probes of these superstring phases that we have seen peaking at high frequencies. And a key important detail there that moduli domination eras, which are a general expectation, dilute previous signals. So faster decays give better chances of observing, being able to observe things. Other things that I'm thinking about at the moment, well, from this scenario, kind of a very question that one can think of is, okay, what happens if we allow for interactions between this population? Does this change much the whole picture and so on? Also, the idea of enhanced moduli decays, whether there are any maybe resonances that could be taking place, and shorten these eras and motivating then observable signals from early on. Also, studying the evolution of couplings, not only of the tension of cosmic strings, but other couplings are also affected by moduli evolution. And also the possibility of primordial black hole formation, right, in these different alternative cosmological histories early on. And that's all on my part. Thank you very much for listening today.
Thank you very much for the nice talk. So we have some time for questions for Nolia. Are there any questions for the speaker? Yeah, Ivana.
Hi, sorry, I was muted. Can you hear me now? Yeah.
Yes.
Hi. Yeah, well, I wanted to ask, like, I noticed this ratio, like 3-to-1 ratio in this loop tracker solution, right? Of the omega factors. How sensitive is it to like changing the starting parameters of the module, like the exponents and the tension and so on?
Okay, so meaning this fraction that you get in the cosmic string loop tracker for the density loops, right?
Yeah.
Yeah, so basically these 3/4 arises from the beta, like it's particular to the F strings coupled to the volume modulus. In the paper, like we computed for a general beta the existence of this fixed point and the conditions for it, but it would depend on the coefficient beta, like on the dependence on the coupling between these two things, right? Whether this can arise. Yeah, if I remember correctly, I think it was the omega of the loops was something like beta square over 4 or something like this. Yeah. So yeah.
All right. Thank you.
Thank you.
Okay, if there are no other questions, maybe we can stop and thank Nolia